Hello everyone, welcome to the video lecture series of Learning Theory of Automata and Formal Languages. My name is Binayak Parashar. I am working as an assistant professor in the Department of Computer Science and Engineering at Ajay Kumar Garg Engineering College. So we are into unit number 1 and we are learning about the basics and fundamental concepts of finite automata. So till now we have tried to understand the concept of the basic topics like what is the meaning of finite automata without output that comprises of DFA, NFA, epsilon and FA. We have seen their conversions, or you can say their equivalence properties. We have tried to check it out. What is the concept about? What is the concept of finite automata with output? That is nothing but Mealy and Mealy machine. So in the previous video, if you have not gone through, then please look into the previous video. Then only you'll be able to understand what is the concept behind this particular topic known as finite automata with output. Okay. So in the previous video, we have tried to understand the concept of Mealy and Mealy machine. Now this is lecture number 8 and we are trying to come up with the concept of equivalence of Mealy and Mealy machine. And this is the concept. So if we talk about Mealy and Mealy machine, we have tried to analyze what is the basic definition of Mealy machine, what is the basic definition of Mealy machine, how to construct a Mealy machine, how to construct a Mealy machine, correct? Right now, we are in a state of understanding that how this particular machines can be converted to each other. If we can convert to each other, then we can directly say that yes, both are equivalent to each other. Otherwise, we already know that these two machines comes under finite automata, which are comprising not with final states or accepting states, but with the concept of final output, okay, output alphabet. So these output alphabet will decide that what is the acceptable string that is being given by the language, and this final output will be designated either with the states or with the transitions. So let's check it out. What are the contents of this particular concept? We will try to look into this particular video how to convert a Mealy to Mealy and Mealy to Mealy. Okay. So let's first check it out. What is the finite automata classification? We have done in the previous video also. I'm just trying it to remind you that this finite automata comprises of two categories: with output and without output. If we talk about with output, comprises of Mealy and Mealy machines, which we have seen in the previous video. If you have not seen, please refer back to the previous video where we have also discussed how to design them. And if we talk about without output, DFA, that is deterministic finite automata, non-deterministic finite automata, and NFA with epsilon transitions. So this is the general hierarchy of finite automata. Okay. Based on this, your questionnaires will be coming in your examination. You have to prepare accordingly. Okay, but if we look in a frequent way, we have to first focus how to convert a language or how to design a machine for a particular language. That is our first target. If till now this is your first video that you are looking into, please I would request you that you first check the video number 1 and video number 2, where we have tried to understand how to construct a machine from a language. That is very important. Without understanding that, we won't be able to understand any of these machines. Okay. So now let's go with the next slide. Next slide says the main concept what we are looking into this video is equivalence property. Now the first point says in the Mealy machine, the output is associated with every state, which we have seen in the previous video. Mealy machine is the machine where output is associated with states. Mealy machine is the machine where output is associated with the present state as well as the input transition. See, the Mealy machine, the output is associated with the input transitions and the present state. Definitely, we need to consider the present state from where the input transition is coming out or going out, right? So that is the prior concern. It is not mentioned over here, but the concept is same. Okay. So you can, either way, you can think of output associated with states known as Mealy, output associated with transitions known as Mealy. Okay. But the equivalence of the Mealy and Mealy machine says that both the machines generate same output for the same input. Definitely. If we need to find the equivalence property of both the machines, then for both the number of inputs, it should represent the same output. That's the only important property to be kept in mind. If it is so, then it is possible to convert the machine from one to each other, or you can say one to another and vice versa, right? But here, one important note that you should keep in, if you are giving any kind of competitive exams, this particular note will help you. If we talk about Murray to Mealy machine, okay, number of states remain same. Number of states remain same. But if we compare Mealy to Murray machine, then number of states will increases. We will try to look into with a practical demonstration. Again, I am telling, from Murray to Mealy machine, number of states will remain same. From Mealy to Murray machine, number of states will increases, not decreases, not same. Okay. Yes, sometimes it might be same, but we will look into that once we are come across with different types of examples. Okay. Now the method, generally what the method says, how to convert this. Okay. The method generally says the same concept what the equivalence property is all about. Here what it says, we are having a machine, okay, and that machine can be a Murray machine. So suppose the equivalent Mealy machine and represented by M dash. So here we are taking M as a Murray machine and M dash as a Mealy machine. The output function delta dash can be obtained as this one, okay, equals to, that means nothing but if we are talking about the same input, it should comprises of the same output. Same input, it should comprise of the same output. So if this happens, then we can say that both the machines are equivalent. Now what this transition function says, let's define with an example. Okay, let's take an example, and this is what I'm trying to convert a Murray machine into a Mealy machine. Okay, so what are the steps involved? Let's check it out. The first step says, if the transition diagram is given, then convert the transition diagram to transition table. Okay, now if we have understood how to design a Murray machine, if we have understood how to identify that that machine is a Murray or Mealy, I think you can guess from here that what is it is a Murray or it is a Mealy machine. You can pause the video, you can think of it. Here output, this is the output, right? Output is associated with states. Whenever output is associated with states, then keep in mind that that is nothing but what? Murray machine. Sometimes in your question it will not be given that convert the given Murray machine to a Mealy machine. It will directly ask that find out the equivalent machine of the given diagram. So you need to find out, you need to first identify whether that machine is a Murray or Mealy. Once we have done it, we need to convert this transition diagram into transition table. Let's check it out how to convert. States are what? Q0, then and Q1. So two states are there, okay, Q0 and Q1, and Q0 being an initial state I have given. Okay, now Q0 on seeing A, where it is going to itself. Q0 on seeing B, where it is going to Q1. Q1 on seeing A, it is coming back to Q0, and Q1 on seeing B, where it is going to itself. Okay, and output associated with Q0 and output associated with Q1 is what? 0 and 1. That's the transition table. Okay. Next step says, then in the second step, convert the transition table of the Murray machine to transition diagram of the Mealy machine, where the output will be associated with the transitions. So for this, I have discussed with you in the previous video, where I have first drawn the Murray machine design. Then I have told you that from the Murray machine, how to identify that that we can convert into Mealy machine. See, it says that second step says that the transition table of the Murray machine to transition diagram of Mealy machine. Transition table of Murray machine to transition diagram of Mealy machine. Let's check it out. What are the states? Q0 and Q1 only. So let me draw this Q0. Let me draw this Q1. So this is the initial state. I know that the output is not will not be associated with the states. Output will be associated with the input transitions. So now let's check Q0 on seeing A, where it is going to itself, correct? Then Q0 on seeing B, where it is going to Q1. Next, Q1 on seeing A, where it is going? Q1 on seeing A, it is going to Q0. Then Q1 on seeing B, where it is going? Q1. I have drawn it. Now how to find out that which transition is coming on which one? See, A is the transition entering where? Q0. What is the output of Q0? Output of Q0 is 0. So I will not write here, sorry. I will be writing where? I will be writing over here. Then next, A, where it is entering? I am just considering the incoming edges to this state. Incoming edge of Q0 is which one? A. Once I have already done. this will be 0. What is the output of Q1? Output of Q1 is 1. So incoming edges of Q1 will be B/1, B/1. So this is your Mealy machine. That's it. Now from here you can design the transition table of the Mealy machine and you can stop it. So this is how you need to convert a Murray to a Mealy machine. I hope it is clear to everyone. Next concept comes. This is the main important concept where we need to focus. We need to convert a Mealy machine to a Murray machine. Let me get back to my previous slides where I have mentioned a very important point. Whenever you convert Murray to Mealy machine, the number of states remains same, which I have shown it to you, right? Number of states remains same. But in the case of Mealy to Murray machine, number of states will increases. So that means somebody other, this is an important algorithm to follow. Let's check it out how to do it. Step 1 says that if a transition diagram is given to you, then convert the transition diagram into transition table as similar to Murray to Mealy. Here we are trying to look into Mealy to Murray. In step number 2, from the transition table of Mealy machine, find out such kind of states which are showing more than one outputs. This is the important point where I have to stop and let me take an example. Then only it will be easy for you to understand. And in step number 3, it says that then in such cases, divide those states into more number of states depending on the outputs associated with them. Suppose I say I am having two fingers, this finger is associated with one output and this finger is associated with one output. But this is my hand, correct? What I will try to do, I will try to designate this hand into two categories. In two categories, one category will designate the output which is associated with this and the other one will be categorized with the output which is associated with this. So this is the way you need to categorize those outputs. Let me check elaborately with an example for step number 2 and 3. Okay, let's take an example and let's discuss this. What is the step number 1 says? If you have a transition diagram for it, convert that transition diagram into your transition table. But this is actually the previous conversion. Here I was trying to mention you the steps, but there only I have explained you. No need to worry. So the same concept, same diagram is given to you. So I think you will be getting the same input. But if you want to design the final transition table, this is actually this question is question number. This is for Murray to Mealy machine, which we have already designed over here, and we got this diagram. But finally, if we need to convert this table, this diagram into a table, then how to draw it? See, this is the table that we got it. And let me take the diagram. The diagram is this one. So Q0 and Q1 are the only two states. So I will write Q0 and Q1. Q0 on seeing 0 input. See, this is actually, this is not an input 0. This will be A and this will be B. Okay, A and B, because inputs are A and B. Outputs are 0 and 1. Okay, outputs are 0 and 1. 0 and 1. Outputs are 0 and 1. Inputs are A and B. Okay, this is a mistake. So Q0 on seeing A, where it is going? Q0 on seeing A, it is coming back to itself. Okay, Q0 on seeing B, where it is going? Q0 on seeing B, Q1. Okay, then Q0 on seeing A, Q1 on seeing A, it is coming back to Q0. And Q1 on seeing B, it is going back to itself. Okay, so this is what the diagram was all about, right? I got the transition table for the Mealy machine. Now we need to just write down the associated output with it. Right? So what is the associated output for Q0? See, Q0 on seeing A, it is coming back to Q0 with an output of 0. Correct? Q0 on seeing B, it is coming back to Q1. Correct? Whose output is what? 1. Like this you need to find it out. Then let me check. Q1 on seeing A, it is going back to Q0, whose output is what? 0. Then Q1 on seeing B, where it is coming back to itself, whose output is what? 1. That's it. So this is the final diagram for it. Sometimes in the Mealy machine table, you might get some sort of sets which are having different outputs. Now here Q0 is designated with 0 only. So there is no problem. Okay. But sometimes you might get particular table where the states will be the same, but the outputs will be different. In that scenario, you need to divide. I will let you know how to do it. Let me take the second example where we are going to discuss about the conversion table for Mealy to Murray machine. Okay, as this table is Mealy machine, because in output is associated with the input transitions. Okay, so how to design it? first I need to take this particular table into your transition table, right? First before that we need to check which are the states having two different outputs. See, first let me take for Q naught. If we look into these particular states, for Q naught is associated with 1 here. Q naught is associated with 1. So Q naught output will be what? 1. Fix. Okay. Next come back to Q1. Q1 output is 1 and Q1 output is what? 0. Oh, sorry. Q1 output is 0. Q1 output is what? 1. So that means Q1 is having two outputs. One is 1 and one is 0 and one is 1. Correct? In that scenario, what they have said, if find out such kind of states which are showing more than one outputs, then in such cases divide those states into more number of states depending on the outputs associated with them. So I will try to now define this as Q10, Q11. How I have defined? Q10, Q11. This is the nomenclature that I have followed. You can take any name nomenclature. Okay. Next comes Q2. Q2 here for input 0, it is having, sorry, this will be input A and this is input B. Okay. For input A, Q2 is showing output as 1 and here Q2 is showing output as what? 0. Now Q2 will be again defined with two different outputs. So I will not name as Q2 0 and Q2 1. I hope it is clear. Next comes Q3. For Q3 it is 0. For Q3 it is 0. So Q3 output will be 0. So this is the overall analysis that I have got from step number 2 and step number 3. I hope now till it is clear. Now it will be easy for you to make you understand this. Now how many states we are having? 1, 2, 3, 4, 5 and 6. Not this one. This one has been divided into two states. So 1, 2, 3, 4, 5, 6. Write down names of it. So Q naught, Q10, Q11, Q20, Q21 and Q3. Which is the initial state? Initial state is this one. There is no final states. Remember, there is no final states, only the output will designate your final outcome. So Q naught on sync A. Now I have to go over here. Q naught on sync A, where it is coming? It is coming back to Q3, whose output is stable. Output is stable, no? Output is stable. So Q naught on sync A, it is going back to Q3, and Q naught outputs I will write it down later. First I'm just writing the transitions, okay? Because it's a Murray machine. Then Q naught on sync B. Q naught on sync B, where it is going? It is going to Q1, which is having output as 1. Which is the state having output as 1? Q11. So I will write down as Q11. I hope now it is clear. Next, I have to check Q10. Always remember, these two states will have the same transitions. Only one particular thing you need to check it out. This means what? Q10 or Q11 means what? Q1 state only. So let me get back to here. Q1 on sync A, where it is going? It is going to Q0, and Q0 output is stable. Q0 output is stable. So what I will write here? Q0. If it is Q0, here also it will be Q0, because both are corresponding the same states. Next comes Q1 on sync B input. It is going to Q3, whose output is also stable. Correct? So I will write down as Q3. So Q1 is done. Now come back to Q2. Q2 on sync A, where it is going? It is going to Q2, whose output is 1. Q2 whose output is 1. That means Q21. So Q21. Okay. Next, Q2 on sync input B, where it is going? It is going to Q2, whose output is 0. Q2 whose output is 0. Q2 0. So same thing will be written over here. And finally, we are left out with Q3. If you remember Q3 on sync input A, it is going to Q1, whose output is 0. Q1 whose output is 0 is Q1 0. And Q3 on sync input B, it is going to Q0. Q0 his output is 1, which is stable. So it will be Q0. So all the things are done. What I need to do? I just simply need to write down the output of each states. So what is the output of Q0? 1. What is the output of Q10? Q10 is 0, then 1, then 0, then 1, then 0. So it will be 1, 0, 1, 0, 1. What is the output of Q3? It is 0. So this is the final table. See, I have taken one more table. Why I have shown you one more table? Because if you look into this particular table, first I am not considering this output. First I am trying to check the transition. So here what you can do, you can draw a particular column over here and write down the designated outputs for every states. And then finally write down over here. That is the way of writing in your examination. But I have skipped one particular step and I have directly shown this concept over here. Okay, sorry, directly this concept over here. I haven't drawn one more column where all the outputs states are associated. No, I have not drawn that. I have directly taken the output. So this is how you can convert a Mealy to a Murray machine. Only the one thing that you need to consider, that you need to find out certain states where the outputs are different for different inputs. If you get, then they divide those kind of states into one kind of nomenclature that you want. I have defined as Q10, you can write down Q M, Q, N, so whatever you want, but this is not at all mentioned. You just need to divide those states as mentioned in step number 3. Okay, so I hope in this particular video you have tried to understand the overall concept of this particular Murray to Mealy machine conversion and Mealy to Murray machine conversion, correct? In the upcoming lectures, we will try to find out how to identify or how to get back from this Murray concept or Mealy concept, and how to divide a final DFA into a smaller DFA. That is nothing but minimization of a DFA, which we will be looking into lecture number 9. In that particular video, we will try to understand that if we are having a bigger DFA or bigger finite machine, how to optimize that, how to minimize that, okay? Because if we particularly divide a particular machine and we get the same language, then why not to get a particular machine which comprises of lesser number of states, correct? That is said to be optimization. So we will try to do that particular concept in the next upcoming video, and there we will try to check what algorithm it follows, okay? So therefore, in this particular video, we have tried to understand the concept of equivalence of Murray machine. We have tried to check what are the different types of finite automata, with output, without output, just a basic introduction. Already we have seen on a whole of it. We have seen how the equivalence property is all about. This is a very important point. Keep in mind that in Murray to Mealy conversion, number of states remains same. In Mealy to Murray conversion, number of states increases, okay? Next, we have tried to find out the method in a you can say formal description way. Then we have seen the steps, and in the steps only I have defined a example. That's not a matter. So in the steps we need to follow out. For Murray to Mealy, it's very easy. Just if a transition diagram is given to you, convert that into transition table, and for a transition table you designate the transitions, and then finally write down the outputs based on the states. That's it. Okay. Then in case of Mealy to Murray machine, just you need to focus two things, that if you find any kind of states which are showing more number of outputs, then you need to differentiate those states into any nomenclature, so that those states will have their own association with the outputs, okay? And then finally I have shown you an example how to convert it. So this is all about your today's video. I hope you have understood. In the next video, we'll come up with another interesting topic, which is known as minimization of a finite automata. So thank you for watching the video.